Good morning. Not too big a crowd here in the classroom. Anyway, I wanted to introduce the exam review that Robert is going to go through in detail. I just want to point out that due to a series of communication issues, misunderstandings on my part, and I take full blame, there were some problems with the exam questions you got. And Robert and I went over the whole thing, and there could have been a number of different ways to rephrase the exam, but we decided to rephrase it in the way you're going to see. So essentially, Robert is going to go over the exam in a slightly different way than what you saw. And I want to point out that nobody lost grades because of that. So everybody got full grades for any misunderstandings of any of the issues in the exam. So I'm going to let Robert go over what the exam should have said and should have asked, and he's going to go through all the solutions. If anybody has issues, please, you can first talk to Robert. And if you still have an issue, come see me. But the bottom line is nobody will lose a point over this issue. And I think this particular exam is very interesting, and there's a lot one can learn from the solution to the exam. So without further ado, I'm going to let Robert take over, and after Robert has gone through the exam and the solutions, I will pick up with the lecture after this. Here you go.
Okay, can everybody hear me? All right, sounds like it. Okay, overall, you guys did pretty well on the exam. So there were 38 total points. The average score was about a 33, just under a 33. So that's an 87%, which is really high. Median was 34.5, and then several students got perfect scores. So that was great. So good job to everyone. That's about it. That's all we're going to go over for the exam grades. Moving on. Like Professor Donath said, there was a bit of communication error, so we apologize for that. But like he also said, no one was punished with their grades for that. We made sure that if you showed understanding how to place origins, how to do the DH table, and how to write your A matrices, that you didn't lose any extra points, and you're actually given points for our mistake. So anyway, the main difference here, if you remember this figure from the exam, there were only 3 origins for you to place, O1, O2, and O3. In order to actually solve this problem correctly, you had to have an origin 4, which some students brought up during the exam. The reason we didn't include an origin 4 initially is because we're not considering a joint at the end effector. So really there shouldn't be a need for another origin. However, we need to get the z coordinate aligned with the z coordinate at the end effector. And the first solution with only 3 origins didn't have the z aligned. So really, to solve the problem the right way and get the right transformation matrix, we had to include another origin. So that was the big mistake on our part. So essentially, if you showed understanding up until placing origin 3 and drawing coordinate frame 3, you should have gotten full points because there shouldn't have been any confusion up until that point. Okay? So part A was pretty simple. It was a transformation matrix from the origin R, the robot frame, to the base coordinate frame. So if we're going to switch to the solutions here for a second. there was one rotation, and it was 180 degrees about r. So, or about z sub r, my mistake. So, using this view, we can see that zr and z sub 0 are pointing in the same direction, they're parallel. And to get that y sub r aligned with y sub 0, it's just a 180 degree rotation about z sub r. So pretty simple right-hand rule to figure that out. That's where this 180 degree rotation comes from. And then this R matrix, this rotation matrix, is for rotations about z. So just plug in 180 degrees and you get the first 3 by 3. And then the position vector. So we have a 0 degree or 0 translation from xr, negative 14 from yr, and 2 from z sub r. So again, going back to the diagram, we can see that if we zoom in here, that's a little blurry, but x sub r is normal to the distance or the displacement between the two origins. So there's no translation in x. If we look at the top view, there's a 14, these are inches, I'll just go with inches. There's a 14-inch displacement between OR and O sub 0, but since Y sub R is pointing away from origin 0, it's a negative 14. And then lastly, if we go back to the side view, Z sub R is pointing directly towards O sub 0 along that joint, and this distance is 2. So the translation in Z sub R is positive 2. And that is where this position vector came from. Any questions? Okay. Moving on. Most people got part A and part B right. Part B was the unit vectors. This was pretty simple. So the unit vector to joint 1 had a 1 in the z direction. And we can see that from coordinate frame 0, z sub 0 is in the direction of joint 1. So z is positive 1 for the coordinate frame, or for the unit vector, sorry. And joints 2, joints 3, and joint 4 are all normal to the page, which is in the y sub 0 direction. So all the unit vectors to joints 2, 3, and 4 are just a positive 1 for y. Does that make sense? All right. Okay, part C is where some of the confusion started, I think, for some students. So this is where we have to place origins. And actually, up until through origin 3, it should have been pretty simple. So here's a solution. So origin 0 is already placed, just to give you guys a freebie there. We know origin 1 had to fall along joint 2, or the axis of rotation of joint 2. That's the first rule. So in the side view, we know it has to be at this point, just because joint 2 is normal to the page. And then in the top view, origin 1, again, along joint 2, and had to fall in line with origin 0. So along this, this dashed line that's horizontal, pretty much all the origins fell along that line. Origin 2 and origin 3 are same story as origin 1. They fall on joints that are normal to the page. So in the side view, they're all going to be right on the joint axis. And then in the top view, they all have to line up with each other. So O3, O2, O1 all lie on this dashed line. And for the exam you took, that's as far as you had to go for placing origins. But in order to get the true correct answer, again, we added an origin 4. So in the top view, origin 4 had to line up with origin 3, so somewhere on this dashed line. And then it had to be in line with, the z direction of origin 4 is going to have to line up with the z direction of origin E. So it has to be along this vertical line that represents the instrument shaft. So we placed it right here. This is blurry, but you can see we placed it right here, which would place it right above the origin E on the top view as well. And again, you did not have to do that on the exam. If you tried placing an origin 4, you were given full points. As long as you got through origin 3 correctly, you were given full points. And then the other part of this question was finding the coordinate frames. So here's that. You were given coordinate frame 0 and coordinate frame R. So we'll start with coordinate frame 1. We know that z sub 1 has to fall along the axis of rotation of joint 2 because, again, origin 1 is at joint 2. And since joint 2 is normal to the page, z1 is normal to the page. So these arrows are just going to be either x or y. And then, let's see, y1 has to be parallel to joint 1. That's another rule. So in this view, joint 1 is at this 45-degree angle from the horizontal, which means y1 is also going to be in that same direction, which is where we get y1 here. And then since we have z and y, we can just find x. That's how I solved that one. Any questions so far? All right. For origin 2, it's pretty much the same thing. So z2 has to fall along the axis of rotation of joint 3, which is, again, normal to the page in the side view. And then this is one of those situations where y2 can't be normal to j2. I went over this in the review slides. x2, so one of the rules when this happens is that x2 has to pretty much be in a direction that connects the previous origin and the new origin. So origin 1 and origin 2, x2 has to be in some direction along this line. So that's where I got x2. So in this situation, you solve for z and x first, and then place y based on those. For coordinate frame 3, we have origin 3 along joint 4's axis of rotation. And this is a similar situation where x has to connect or has to be in a direction that connects joint or origin 2 and origin 3. So if you can see my cursor, it has to fall along this dashed line, which is where x3 comes in. And then since we know z3 is into or out of the page, we can just use the right-hand rule to find y3. So if you got all of those, if you got everything correct up to this point, you were given full credit for this question. I'm just going to go through how Professor Donath and I solved for coordinate frame 4. So this diagram is how we did it. So I placed coordinate frame 3 here, and this is just offset, so it's a little more clear. But coordinate frame 3 is placed at joint 4, and then we know that the z direction of coordinate frame 4 is going to have to line up with the z direction of coordinate frame E. So we know that origin 4 has to fall along this vertical line to fall in line with origin E. Based on that, let's see. we wanted this final translation between 4 and e to be just a d in the DH table. So x4 and xe line up as well. And then obviously y4 is just going to be, let's see, what would that be? It'd be out of the page. Same with y sub e. And placing it here gave us the correct transformation matrix later on in the exam. Are there any questions how we got this origin 4 or coordinate frame 4? And again, if you got up through origin 3, you were given full points, so no need to worry there. All right, we'll continue on. So we're through part C. Part D was the DH table, and again, a lot of students had a different answer for joint 4, but if you showed you knew how to do the DH table through joint 3, you were given full credit. And we added another row here, which obviously was not there in the exam. But you need this extra row because we added an origin 4. Okay, so I will run through how we solved for the DH table. Let's see, joint 1, we start with theta 1, which is the rotation about z sub 0 to move from coordinate frame 0 to coordinate frame 1. And there is no rotation about z. Let's go back. Okay, again, moving from this coordinate frame 0 to coordinate frame 1, there was no rotation about z. We had a positive 90-degree rotation about x sub 0. So if you do the right-hand rule, that will get y sub 1 pointing down like it is here. So the only rotations for joint 1 was positive 90 degrees about x, which is the alpha value. And then to find d and a, so d sub 1 is the distance. The way I solve it is the distance in the y sub 1 direction from origin 0 to origin 1. So again, y sub 1 is pointing down and to the right. And if we go back to the diagram with the dimensions, y sub 1 would be pointing down and to the right. And the distance in that direction from origin 0 to origin 1 is this positive 18. And then a sub 1 is the distance in the x sub 1 direction from between the two origins. So if we go back to the coordinate frames, x sub 1 is pointing up and to the left, or up and to the right. And this pointing up and to the right, this distance is 5. But since we're looking at moving from origin 0 to origin 1, this value is actually going to be a negative 5 because x sub 1 is pointing back towards origin 0. So d and a are going to be positive 18 and then negative 5. Anybody got questions on that? Okay. For joint 2, theta sub 2 is the rotation about z sub 1 to get from origin 1 to origin 2. As you can see, the coordinate frames are set up the exact same. So there's not going to be a rotation about z or x. So theta and alpha are both 0. And then d sub 2 is going to be distance in the y2 direction from origin 1 to origin 2. And if we go back to the solution, origin 1's here, origin 2 is here, and y2 is pointing down and to the right. So there's actually no distance along y sub 2. That's why d2 is 0. And then in the x2 is pointing up and to the right. So since a sub 2 is the distance in the x2 direction from origin 1 to origin 2, that's going to be positive 12. So it's 0, 0, 0, and 12. And then the joint 3, looking at theta, it's the rotation about z2. So again, z is into the page for frame 2 and frame 3. And since frame 3 is a little different orientation than frame 2, but x and y are still in the plane, we know there's a rotation about z. So a positive 90 degree or a 90 degree counterclockwise rotation about z2 lines up x2 with x3 and y2 with y3. So theta 3 is 90, and there's no rotation about x, so alpha 3 is just 0. D3 is going to be distance in the y3 direction from origin 2 to origin 3. So going back up to the diagram, y sub 3 is pointing down and to the left, and that's normal to the direct or the displacement between origin 2 and origin 3. So d sub 3 is also 0. And then finally, x sub 3 is pointing down and to the right, and a sub 3 is the distance in that direction from origin 2 to origin 3, which is a positive 12, as seen here. So we're going to have a 90 degree rotation for theta, 0 for alpha, no d, and 12 inches for joint 3. And to reiterate, if you showed that you knew how to do the DH table, you got joints 1, joint 2, and joint 3 correct, you were given full points for joint 4, no matter what you put. We're still going to solve for joint 4, though. The way we solve for it up here, so y sub 3, x sub 3, and then we need to get z sub 4 in the plane, so we know there's going to be a non-zero alpha. The first step is solving for theta, which is, again, rotation about z sub 3, which is into the page here. And if you remember, the goal of this rotation is to get x sub 3 and x sub 4 parallel. So we have to rotate 45 degrees to get x sub 3 along the horizontal. And when we do that, y sub 3 is pointing down. And we know we need to get z4 pointing down, so there has to be a rotation about x sub 3. And that's going to be negative 90 degrees. Yep. So that's how we get the angles for joint 4. And then for D4, there is no distance between origin 3 and origin 4 along y4, because y4 is now coming out of the page and they're collinear in the plane. So D4 is 0. And then A4 is, since there's a 45 degree offset here, A4, we're finding the hypotenuse of this triangle, and that's just 4.24 inches. And then the last row is just translation from joint 4 to joint E, or origin 4 to origin E. Since the coordinate frames are now lined up, there's just a 5.5 inch translation, and that's the D value. So that's how we solve the DH table. Again, everyone's going to have a different answer for joint 4 most likely, because there was some confusion. But if you showed you knew how to do it from joint 1, joint 2, and joint 3, you were given the points for joint 4. So we want to make sure no one was punished for our mistake. This new exam, since there's another row of the DH table, we added a matrix to find. And this is pretty simple. It's just plug and chug from the DH table. So there's a few examples where students got wrong answers in the DH table, but they still found the A matrices correctly based on their DH table values. You were given, I think, half credit for knowing how to do it, having the correct method. There's a small, you lost some points though for having the wrong DH table. But anyway, again, it's just plug and chug. No need to really go over how we got it. As long as you did the correct method, which is this matrix right here, you likely got full points. All right, part F was just a matrix multiplication sequence to find the transformation matrix from the robot frame to coordinate frame 3. So we solved for the transformation from R to 0 in part A. So that's the first step. And then just multiplying by 3 A matrices, you see the zeros, the 1s, and the 2s cancel. And we're left with the transformation from R to 3. This one was pretty straightforward. Anybody have questions about that or anything else I've gone over? All right. Moving on, part G. This was one where you had to multiply, in the real exam you took, you were given TR3, which were given here, and then you had to multiply that by the A matrix from 3 to E. The problem with that is that everyone had not everyone, but since there was a problem with the exam, this joint 4 row of the DH table was so different for everyone. And that's where you got the A matrix from 3 to E. So there were a wide range of answers for part G. So if you showed the correct multiplication sequence, you were given full points for this part. So it didn't really matter what your final answer was as long as you showed that you knew how to move or how to get that transformation. That's all you needed to show. For this exam, though, since we added a row and there's now a A matrix from origin 4 to origin E, we'd have to multiply the transformation from R to 3 times 2 A matrices, as seen here. And this is the final answer. And one way to check, so a few students actually brought this up during the exam, but when they solved this transformation matrix, they got a y that was not negative 14. And if we go back to the diagram on this top view, since all of these origins are in line, we know that the position vector or the distance in y sub r to the end effector has to be negative 14. So there are a few students that brought that up. That was kind of what tipped me off that there might have been a problem here, because like intuitively this has to be negative 14 just based on the schematic. Obviously these x and y, it's a little more difficult to solve just because there's some geometry and whatnot, but since there's a negative 14 here, that should tell us that this is likely the correct transformation matrix. To reiterate, if you showed the correct multiplication sequence, you're awarded full credit for this part, though. The last part of problem 1, this kind of tested your understanding of the robot, and it made sure you were reading about it in our description. So if we're considering a situation where, let's say the joint angles are non-zero, meaning that this schematic looks different. Let's say it could be anything. There could be joint 2, joint 3, and joint 4 at a different angle. The question is asking, what about this transformation matrix has to stay the same? And the position vector cannot change. And that's because the if you remember, I'm not sure if anyone really remembers about the robot, but the trocar here is where the end effector is, and that is stationary in the port, which is essentially the incision in the patient, and we're considering that as like a spherical joint about the port. So it can twist all sorts of ways, but it cannot move, it cannot translate anywhere, because in a surgery that would rip the patient's skin or do some sort of damage. So we were looking for something about the position vector. There were a lot of students that said like the Z had to stay the same. If you were one of those students, you were given partial credit, but really the entire vector itself can't change, no matter what joint angles you have. Is that clear?
So if we didn't have the negative 6.11 or whatever, it's fine as long as we said it was like Px, Py.
Yeah, you got full points for that. If you said position vector, if you said Px, Py, Pz, if you put your values but they didn't match up with what I had, it didn't matter. You still got full points.
So the question I have about the test in general. So if you mess up something with like a coordinate frame, which leads to a wrong transformation of the DH table, but you did the same process correct, which then led to you the wrong answer in the matrix multiplication. Like, is that kind of, that's probably a severe mistake.
Well, matrix multiplication for part G, if you had the right sequence, you got full points. If you did a coordinate frame wrong, it cost you a little bit. You still got some credit for doing the correct method, as in like the DH table and the A matrices. Does that make sense?
Yeah.
Okay, so I get that, like, this is kind of a step-by-step, like each step depends on the previous step. So if you placed origins wrong, that's going to affect everything. If you do wrong coordinate frames, it's going to affect things. But we tried giving partial credit for your method. Make sense?
Yeah.
And if you go through your exam and you have an issue with it, just let me know, and I'll try and work that out. If there aren't any questions on question 1, we'll move on to problem 2. And this was just roll, pitch, yaw, multiple conventions. There were a bunch of right answers I saw for part A. So, I mean, most people got this question completely right. I just listed 3 solutions I saw in the exam that gave the right orientation of the coordinate frame 4 here. For part B, there's 2 possible situations given here. So some students did an X, Y, Z rotation, and then some students did a Z, Y, X rotation, both of which were fine. They were correct answers. I just listed 2 Z, Y, X rotations here that are correct. Anyone have any questions about the roll, pitch, yaw? It seems like the class was pretty clear on this concept, which is good to see. Okay, I guess that's all I have. You guys did pretty well, I think better than when I took the exam, so good job. Again, I apologize, there was some confusion, but we made sure that no one was punished for our lack of communication. So, yeah, sorry about that, but it shouldn't have impacted anybody's scores. If you feel like it did, please reach out to me and we'll work it out. Okay?
Anyway, first of all, the robot used for that assistive surgery, that's an actual machine in the surgery center here at the university. The pictures are from that lab. We were allowed to go into the lab for a limited period of time. We were not allowed to take any measurements. We had to basically make all sorts of assumptions looking at what we saw there and doing some YouTube, looking at a whole bunch of YouTube videos of the machine. If you go to the website of the manufacturer of that robot, lots of hand waving, but they never really show you much detail about the machine. They're very protective because, as I understand it, their patents have all expired, and they're worried about all sorts of competition. And I believe 3M and Medtronic are entering the field of robot-assisted surgery. So they're very careful and don't want to talk to a lot of people. I should point out that a number of years ago, I won't say what year, but we had an exam that dealt with this type of surgical device, a predecessor of the company that now makes these the particular machines used in the exam. And if I remember correctly, the TA that year was actually hired by that company when they graduated and moved off to California. Anyway, it's an interesting machine, and What I do suggest, we're going to post the solution on the web. I do want to go over with Robert a few little things before he posts them, so it won't show up quite yet this afternoon, but I hope it'll be posted by tonight so you can take a look at it. I do appreciate that you need to spend some time looking at it. You can't just follow it all in the few minutes that he was presenting it. You need to do your own thing with understanding where the X, Y, Z's move their way around from beginning to the final E vector where the trocar is in the machine. On today's Thursday. Next Tuesday, I am going to bring some instruments into class. So anybody who's off campus who wants to show up, you can come next Tuesday, and I will bring instrument shafts through. Those instrument shafts add another 5 degrees of freedom. So beyond what you saw in the exam, there are another 5 degrees of freedom that are controlled by the surgeon directly through a teleoperated arrangement. And I will show you what I'm talking about next Tuesday. But that part was not part of the exam, and you don't need to. I didn't want to confuse anybody by getting into all the details of that portion. Anyway, I just want to remind people that today I will be meeting with a few more students. There aren't, right now, according to the list, I only have 5 more students to meet with. I believe there is 1 student who has not signed up. I don't know who that student is. I'd have to go through the class list and then cross-check against everybody I've met. I haven't done that yet, but if you haven't met with me for 15 minutes, then please shoot me an email and we'll set up a time to meet sometime next week. Okay, so please do that, because the last 5 students I'm meeting with are listed here. John Helgeson, Carsten Mueller, Yuha Yu, Noah Olson, and Philip Knopp. And I will see you guys later. So what we're going to do, last week we talked about computing the Jacobian. And I went through this in great detail on a 3-jointed machine, which had the first 2 joints were revolutes, and the 3rd joint was a prismatic joint. And we went through the analysis, and I went through all the vectors and unit vectors and cross products in order to get the final result, which was a 3x6 Jacobian. So the question always is that the only application of Jacobian? Jacobians have, the application that we were talking about essentially leads to the capability of calculating 2 things. Either you know what the joint velocities are, and then you can compute what the final velocity of the end effector is, and think of that as not that different from the forward kinematic solutions, but it's what we would call the differential form. And the other option is to do the inverse kinematics. What happens if I have a specified velocity at the end effector, and I want to calculate what the joint velocities need to be? So to do that, you also have to you have to look at the inverse of the Jacobian. But there are other applications, and the other application that we're going to talk about is looking at the forces. And what I mean by that is, if I have a robot, and now we're talking about a robot that makes contact with the world, I'm doing stuff, and I have to, for example, I got a pen, and I actually am, and I'm not going to write anything, but I am actually making contact with the world, and there's going to be forces that push back. There are reaction forces over here. what is the propagation of these reaction forces to the individual joints? In other words, what is the torque at each joint that either is going to generate the reaction forces, or if I have certain reaction forces that I can measure, what must the joint forces or torques be? Okay, now why is that important? Well, notice I use the word static. We're basically talking about a situation without the dynamics. We'll get to dynamics still in the discussions. When we talk about dynamics, then we need to worry about inertial forces, we need to worry about Coriolis and centrifugal, and all sorts of other forces that play a role. But if I'm talking about static conditions, we're talking relatively slow motions, and we're talking just like if you were doing isometric exercises, and you're pushing up against the wall and exercising yourself, you're not moving through large motions. We're basically talking about think of it being a rigid body in some sense, and we're trying to calculate what the reaction forces in the system are. So what I'm going to first do is show you the complicated way of doing this. And we're just going to go through this just so that you understand the actual complications if you had to actually solve for everything you need to. And I'm doing this so you get the big picture, and then I'm going to show you that there is a very simple, straightforward way of doing the analysis and figuring out the relationship. Okay, so don't get frightened by what you see here, but I just want you to basically see what all the components are if you were really going to do a sum of forces, sum of moments, and then calculate all the reactions. So if I have an actuator, here's an actuator. Think of this maybe as a motor that it's applying a torque, and it's applying a torque to joint I. And remember, when we're talking about joint I, it's about z sub I minus 1. So there's z sub I minus 1. And then we have this link I, which I'm not drawing because if I drew the link, it would basically cover up all the vectors that I'm showing you. But just assume there's a link I that connects this joint with the next joint. And the next joint, if this is z sub I minus 1, this is going to be z sub I. And this link over here is going to be link I plus 1. So here we have link I minus 1. Here's link I, and here's link I plus 1. Okay? And so this is joint I, and this is basically joint I plus 1. And so if we look at all the forces and torques that are going on, and we have not talked about gravity, but if we're beginning to talk about a system that has mass, and right now we're just going to add the gravitational term, and I'm bringing this up because we will bring up gravity, and when we start talking about dynamics, we cannot ignore gravitational terms. Right now, we're going to include it just to explicitly show it, and then later, we can make assumptions. Do we consider the gravitational effect or not? If we're dealing in this direction, gravity is important. If we're moving in this direction and you have suitable bearings to handle all the reaction forces, then the gravitational effect is not that big a deal unless you're talking about a very large mass at the end and you haven't designed your robot appropriately and it's actually flexing under load, in which case, hey, gravity is certainly a big deal. So if we're talking about rigid components, rigid links, no slippage in the joints at all, then we're going to basically have, there is the coordinate system with the center O sub I minus 1, and here's O sub I. So there's O sub I, there's Z sub I, here's O sub I minus 1, there's Z sub I minus 1. Now what we need to add, as soon as we throw in a gravitational term, we're going to have to worry about the centroid. Okay, the centroid of this link, of the mass, essentially the mass effect, basically mass times the gravitational vector, that is going to act through the centroid of that particular link. Calculating where that centroid is not an easy term, not an easy thing, and we're not going to need to calculate it. So for the analysis we're going to talk about, but I'm showing it to you explicitly that if we were going to throw in the gravitational terms, I'm just going to show you where it appears. So what we're going to do is we're going to essentially, there is going to be a reaction force. So we're going to basically look, here is F sub I minus 1 comma I. And here is n sub I minus 1 comma I. So essentially, this is the force vector, and it's explicitly said this, the force vector exerted by link I minus 1 acting on link I at this particular point, O sub I minus 1, and it's with respect to the world coordinate system. So there's a world or a base coordinate system somewhere, and that's why we have these subscripts O or 0 that you see over here. So these are the forces. There's a component in X, a component in Y, and a component in Z. And there are also going to be moments. And as soon as we start dealing with moments, there's going to be essentially, again, that moment vector is 3 components. And the 3 components, it's a moment vector. And again, in this particular case, it's what link I minus 1 applies to link I. And so these are the terms over here. N, and again, this is a 3 by 1, this is a 3 by 1. And if we're going to do a balance of forces, and we're going to do a balance of moments, so we take all the forces in the X direction, all the forces in the Y, and all the forces in Z, and add them up, we're essentially going to end up with this equation. Okay? I'm just moving this up a little bit so you see these other vectors. This is essentially what you can basically say is the reaction forces are going to be the forces applied over here, the forces over here, and essentially, and there is the gravitational force. And so, in effect, this is the first equation. Remember, there's no dynamics. We're talking about static conditions. So there's no motion going on. So essentially, if we do, free body diagrams and work some of the forces, we're going to get this equation. And if we then do the sum of the moments, again, there are moments here and moments here, but we cannot forget the fact that there are also position vectors which basically take us from the origin up here. So this vector r sub I minus 1I is going to connect O sub I minus 1 to O sub I. And so this is the position vector from O sub I minus 1 to O sub I. So that's from here to here. That isn't a big deal to determine for any particular robot. But there is also this other position vector which takes us from origin I over here over to the centroid itself. And so again, that's a position vector, and it plays a role because this is pretty straightforward. You take n sub I minus 1 comma I, subtract off n sub I comma I plus 1, but then you also need the fact that when you take this vector and this vector, you add the two, you basically get a vector from O sub I minus 1 to this position, to the position of the centroid. That's what this is basically saying. And you have to take you have to do the cross product of that vector with essentially the f sub I minus 1, which is this one here. So remember, we're taking the sum of moments about the centroid. So essentially, you have the vector that basically goes, connects this point to this point. You have to take into account the cross product between that and the force, and that's what this term over here is. That gives us another moment that's applied here. And last but not least, in order to get a total balance, we cannot forget that there's also this force vector over here, which is acting on here. So essentially, this force is what link I is applying to link I minus 1 is applying to link I. And this force, notice the minus sign, because it's applying reaction forces on link I. We can't ignore it. So it shows up here, and it is basically a cross product as well. So we have to take all this together. And if you look at the end conditions, you know, the end conditions, the base of the robot, there's going to be some forces and torques that reaction forces at the base of the robot. You might put it in an instrumented platform and then measure those, for example. And then you have the end effector, which may be holding something. This might be a contact probe that you're pushing into the wall, for example. It might be a piece of chalk on scratching across a blackboard. It is doing some activity where you're interacting with the world, and so there is going to be a force and torque that's applied by the outside world back on the robot itself. Now, we're going to take a look at some examples later on. I'm going to take you to some websites, but there are companies who basically, their mission is to be able to control exactly what the forces and torques are as you apply a surface. And typically, grinding is such an application. There is robot-controlled grinding of surfaces, polishing of surfaces. There are many activities where you actually have to apply forces in a controlled manner to a surface. And what you might be doing is pushing with a constant force against the surface here and not applying any force in that direction. Again, depending upon what the objective is with your tool. Well, if we take all of this together, we take all these equations, spell everything out, and write it out, we're going to get an unbelievable amount of equations. Because remember, if we just look at the forces, we're going to end up, if they're n joints, they're going to be 6 times n unknowns, just from the forces. 3 n unknowns, and then we add the moments, we're going to get another 3 n unknowns. Together, we have 6 times the number of joint unknowns that we're trying to solve. And it can be solved. Very tedious process. You just don't want to bother to do all that, because remember, some simple things like how do you determine exactly where the centroid is inside each link? That's an awfully tedious task to do, and I'm not proposing that we do it. So what we're going to look is we're going to essentially simplify our world, and we're going to simplify our world remembering that we have real bearings, we have structures that are designed to limit all these cross-structural effects. And so we're going to find that there's a much simplified way of relating the torques or forces at the joints with the forces and torques at the end effector. So let's go through this and take a look at a prismatic joint and a revolute joint. And this is going to be what you might call a generic joint. Okay? When I say a generic joint, it's basically assume for a moment that at that joint we're going to have an actuator of some kind, and that actuator might be a prismatic actuator, a hydraulic cylinder that's moving in and out, or it might be a rotational motor. And we're going to assume now that there are bearings and structural elements that basically allow you to ignore all the other reactions that may be applied to that structural joint. So if we take a look at the relationship, if we take a look simply, here's a prismatic joint that can only move up and down, okay? We're assuming that you've designed the structure that if there are any torques that are being applied or in other directions, they are captured by bearings or thrust bearings that take care of those. So if we're going to have a unit vector defined along that joint, and there is the origin of that particular coordinate frame system, essentially now in order to keep this as generic as possible, I'm using tau, but tau can represent either a force or a joint, either a force or a torque at joint I. So for a prismatic joint, tau sub I is going to be three forces, essentially F sub x, F sub y, F sub z. So for a prismatic joint, these are going to be forces in directions. B sub I minus 1 is essentially the unit vector along which the prismatic joint is operating. And so in effect, this is the force vector that the actuator has to apply. This it has to apply to overcome the reaction force vector at this particular joint. Okay? And if we're doing this without studying, we're not taking a look at the whole robot right now, we're just looking at an individual joint. This force vector, call it tau sub x, tau sub y, tau sub z, or F sub x, F sub y, F sub z if you like, is going to be the dot product of the unit vector B dotted with the reaction force. Okay? So when we talk about doing a dot product, what does that mean? Can you remember from your previous courses? When taking a dot product between two vectors, what are you doing?
Projecting it, aren't you?
What? That is exactly right. We are basically taking the component of one vector that is projected along the other vector. Does that make sense? You all remember that? So in other words, when I take this dot product, I am looking at what component of this force vector is acting along this unit vector. And if the system is designed well, it should all be acting along that unit vector, but who knows what else is going on in the system. Essentially, this is what we're going to worry in a prismatic joint. All we need to worry about is essentially the component of the forces that are acting along the unit vector of that particular joint. We are going to assume if there are moments, the moments are going to have to be handled by revolute joints, not by prismatic joints. And if you've done appropriate design, you've designed your bearings appropriately, you make sure that that is true, that essentially your prismatic joints are supporting all the forces along those joints, and the revolute joints are in effect handling the torques or moments that show up. So if this is a revolute joint, look at the similarity between this expression and this expression. If it's a revolute joint, again dealing with this over here, the reaction tau sub I in this case is a set of 3 moments, and that is essentially what is being applied by my actuator. Let's say it's a motor. If everything is designed properly and with your transmissions and everything else, this motor, along which axis should that motor be pointing? If we're going to rotate, this is a rotational joint. If this is a rotational joint, and b sub I minus 1 is now the normal unit vector that is telling us about which axis we're rotating, then the torque applied by that motor, by that actuator, that torque is going to essentially be, again, the dot product of whatever set of moments are acting at that joint. It's going to be dotted, so to speak, with the unit vector. So in effect, this revolute joint, the motor, the actuator, and the transmission, whatever is being applied at that particular joint, its mission is basically to handle the components of this motor, the reaction moments that are applied at the joint, but the dot product, which is the components of that moment, acting along or about that particular unit vector. If there are moments that are not in the right direction, as far as the motor is concerned, it does not see them, because the structural elements of the robot, the bearings that are designed in that robot, are such that they are basically passed down to the ground and are never seen or felt by the motor. Now later on, we're actually going to do a pretty detailed analysis where we're going to include the effects of a transmission, but we're going to do that much later on, and I'm going to show you that the transmission ratio in a transmission plays a very important role in robots. We want to have a transmission. The transmission does a lot. That, call it a gear ratio or the transmission ratio. It is going to have a very positive effect on our ability to control and move a load around in space. But for right now, keep in mind, we're dealing with static conditions, no dynamics, and because there are no dynamics, we're not going to be concerned with inertial effects. When we talk about dynamics, we're going to need to worry about inertial effects. We're going to need to worry about Coriolis and centrifugal and all sorts of other things. But we're dealing with a rigid structure. There's no compliance in the joints, or we're going to say no compliance in the transmissions. And in effect, we're dealing with static force conditions. There's no dynamics playing a role. And so for this kind of case, we can take these dot products for whether it's a prismatic joint or a revolute joint, and so we can put it all together, and we're going to have a set we're going to call it the joint torque vector, because quite a few robots are mostly revolute joints, but I'm sorry, we can have a force in there too. So we're generically, the tau is either a force or a torque. We can deal with either of them. And this is a 6x1 if it's 6 joints. If there are 5 joints, n is 5, or 4 joints, there are only going to be 4 of these. And by the same token, the endpoint force and moment, this has to be 6. Okay? So there's going to be 3 forces here and 3 torques, and that's at the endpoint, where essentially the end effector is holding that piece of chalk and working its way across the chalkboard. Those are the reaction forces that are measured either in a load cell at the end effector or measured by a load cell on the blackboard or some other surface. So that's the endpoint force and moment. And the whole idea here is to relate these two. How are they related to one another? Can we calculate what those forces and torque reactions are inside the joints, which you need to worry about, because when you size a motor, you don't just size it for dynamics, you need to also size it for static conditions. Okay? So you need to include both in making any decisions about how big a motor am I going to use to drive a particular machine. So what we're going to look at is the result, and then I'm going to show you how to get this result, that in effect there is a relationship between those set of torques. Again, remember what torques, it could be a force too, but essentially if we're talking about a set of joint torques tau, what we're going to show is it's related to the set of endpoint forces, F, by the transpose of the Jacobian. Okay? And that's a pretty awesome result that makes it very easy. Once you have the Jacobian, calculating the transpose is fairly straightforward. There's no craziness of having to calculate an inverse of a Jacobian. And so this is a fairly straightforward analysis. And this assumes that the definition of a Jacobian, of course it assumes that the definition of a Jacobian is basically, it's a matrix that relates the set of small differential changes at the end effector, d sub p. Remember, d sub p has 6 components, small changes in x, y, and z at the end effector, and 3 small rotations about x, y, and z. And dq are the small changes at the joints. So if I set 5 joints, 6 joints, whatever, there are going to be a whole bunch of these. And if we're dealing with 6 joints, there are going to be 6 of these small changes in joints. So what J does, the Jacobian, it relates small displacements at the end effector with small displacements in each of the joints. So how do we get that? I notice it is 9:12, and we really haven't had a break. Why don't we, because it's already 9:12, why don't we just take a 5-minute break so you can stand up and do whatever you need to do, and we will resume. I wish there were a clock in here, but I have to search on my screen to find the time. And it's in such small print that I barely see it. So anyway, why don't we take a 5-minute break? We'll resume at 9:17 and carry on with this very brief proof, which is fairly straightforward. 9:17. Spell first name? Just to be consistent, what's your email? Yeah. Oh, I see what you're saying, yes. But keep in mind, there are more than one solution.
Yeah.
This is the solution.
Well, there's that's fine. I'm trying to figure out when we talk side. I get that on I can. Yeah, well, I just. Sure. Yeah.
Okay.
Yeah. That's fine. I just love it, but I'm not gonna make a big deal about it. Like less than anything.
No, but it's important for understanding.
Yeah, no, I don't want to make that mistake.
No, I'm with you. I quickly will talk to him and see that, in 30 seconds, I'm not going to remember all
Sure.
stuff.
Yeah.
Okay? So let me pick up with our discussion. I'm kind of, just to point out, I'm trying to move rather quickly. And just to remind you why I'm moving rather quickly, we have only, after this week, we have only 1 week before spring break. Rodney Doctor will be taking over after spring break, and he's going to be lecturing. And I will be coming back for the last few lectures at the end of the course. And why I'm kind of rushing like crazy is I want to get and talk a little bit about load cells today, force torque sensors, which you are using in your robots. I want you to understand what's involved, and I'm going to try to get to that today and no later at the beginning of class on Tuesday. But what I do also want to do is cover impedance control, give you a sense of what that's all about before spring break. And the reason for that is you're going to be involved with the flashlight assembly until I believe it's a week after spring break. And then you're going to move to a vision lab. So you're going to have some vision assignments, and then you're going to actually do a robot vision lab. And at the very end, you're going to come back and do an impedance control experiment, which we have set up, which we will have set up for you. And I want you to get a little bit of intro to that before you walk into the lab, whatever that, I think, last week of class is. Okay? So just to give you the heads up of what's coming, whether I will get to it and cover it on Thursday next week, I'm not sure, but we'll figure it out, and I will be sure to, at no later than my first class back, we'll cover it. So just giving you some heads up. And keep in mind, lab number 3, your memo/report is due, everybody paying attention, tomorrow morning, okay, by 8 a.m. So just keep that in mind. So anyway, let me keep going, and I'm going to move a little quickly here. Yes? Oh, I'm sorry, I disconnected. Apologize for that. It should. There it is. Okay. Okay, and so essentially, we're going to take a look at what's called the principle of virtual work. And essentially what that in essence says, that if we take a look at the whole system, all right, and again, we're talking about a rigid body, everything is rigid, and if we then add up all the energy or work that goes into that object, and then measure all the energy or work that goes out of it, if we're dealing with static conditions, it should balance. It should basically, all the actuators all the actuators, in this case, and actuators, they are basically going to deal with the environment. Again, we're assuming no energy lost in the system. Everything is rigid. And let's take a look at that. This looks like it's a very complicated deal. It isn't as complicated as you think, because at each motor, what do you have? We're going to have a torque. Let's say it's the revolute joints. There's a revolute joint, and we're going to assume that there's a very small, and we'll see, very small angular change at that particular joint. So there's a tau sub I and a del Q sub I. That means at the motor, there's going to be a tiny rotation at the motor and a torque. And together, what is the product of force times displacement? Force times displacement is work, energy, right? Okay. And if I do force times velocity, what do I get? Power. All right? So force times velocity is basically force times the derivative of force times displacement. Okay? We're not talking about power here. We're talking strictly about energy. So essentially, if I have an actuator applying, this is applying energy into my system. And there's going to be at this joint, at this joint, at that joint, there are going to be a bunch of joints in my robot, and each actuator is applying a little bit of work. Let's call it, we're calling it virtual work. And then at the end point, again, this is where the rubber hits the road, where the end effector is making contact with the outside world. There's going to be the moment that's applied to the robot, that's the minus n, and the force vector that's applying to the robot, that's minus F. And at that end effector, we're also going to have a small displacement. We've talked about small displacements at the end effector. That's del x sub E. And the small rotational change are del phi sub E. So this is where the contact is being made with the outside world, and where there are some actual reaction forces applied to the robot at that outside world. So if we now add up all the work going on, the work is essentially, at this point, at the first joint, we're going to have tau 1 times del Q1, right? This is a force or a torque multiplied by a small translation, if it's a prismatic joint, or a small rotation. So force times displacement, as I said, is energy or work. and then we're going to add up the next joint and the next joint and the next joint. At the nth joint, we're going to have the nth actuator apply a force or torque multiplied by the small displacement at that end joint. Okay, that's all the energy going into the system, all the work going into the system. And then some work is to balance all this. We're basically going to say that at the end point, we're going to have a force vector, which is basically it's the reaction. It's being taken out of the system, so to speak. And so this is the force coming out of the system or being absorbed on the outside world, the reaction forces, times del xc. So that's the energy going out. So these are energies coming in. This is energy going out. And this is work going out. So this is the moment time times those small displacements. We can then combine all this, okay? And we can combine it if we take the transpose of a torque vector. Remember, tau is a vector, 1 by n. Okay, 1 by n is tau. And we're going to multiply it by another vector, but this is going to basically be, we take the transpose of a vector that is a column, then becomes a row. All right, the transpose of a column becomes a row. So this is, the tau transpose is essentially a row vector multiplied by a column vector. So this is essentially a product. And minus, and again, it's the same basic thing. We're going to take the force transpose. Again, force is the set of three forces in x, y, and z. And it also combines now the three torques along x, y, and z, multiplied by the small displacements at the end point, which is del p. Now, the whole point of doing this kind of analysis is if we're talking about any particular geometry, essentially we're talking about really tiny displacements of del q and del p. We're basically going to say there's no real work being done by the system. This del work is equal to 0. Okay? Nothing's moving. There really isn't any displacements to speak of in the big picture. Essentially, the robot is making contact with the wall, and then I'm pushing against the wall. There's no work going on. Now, you might say, I as a human, if I'm doing, push-ups, clearly we're doing some work. But just not doing anything and just pushing against the wall, your muscles are actually contracting. There is real work going on inside your muscles, even if you don't see anything of your arm moving along. But the bottom line is, in this analysis, del work is equal to 0. And when we do that, we are going to be able to see that there's a very neat relationship that comes out of this. If the geometrical constraint is simply del p is equal to the Jacobian of del q. Remember what that means? The Jacobian, by definition, relates small changes at the end effector. Small displacement changes at the end effector are related to small changes at the joints. So del q is essentially a vector of small displacements at each joint. Del p are small displacements at the end effector. This is basically a 6 by 1. Del q could be a 3 by 1. It could be a 4 by 1. But if we're talking about 6, then this will be a 6 by 1, and the Jacobian will be a 6 by 6. If del q is only 3 elements, then essentially your Jacobian is going to be 6 by 3. All right? So if we have this geometrical constraint, which is essentially the definition of a Jacobian, then we can do some plugging in. Here is this del work. I'm just going to take this equation, and now I'm going to substitute into this equation for del p. You see this del p over here that my arrow is pointing to? I'm going to replace del p by j del q. And when I do that, I get this equation over here. Del transpose times del q minus f transpose times j times del q. I get this result. And now I can play with my transposes a little bit, if you will, because what I've done is I've pulled out, and basically I've given you some equations for transposes. If you take the transpose of two matrices, of the sum of two, you're going to essentially, it's the same as adding up the transposes. If you take the transpose of a transpose, it's the original matrix by itself. And if you take the product, if you take the transpose of a product AB, then it's equivalent to reordering B and A, and it's the same as taking the transpose of B times the transpose of A. This is important because it applies to this analysis over here, because we've essentially moved del Q to this side. We had to transpose, move it around, taking into account this result here. Then we take the transpose of the difference, and again, taking this account, we get this result. So the bottom line is we get this equation. We're saying delta work is equal to 0. Well, then if del work has to be equal to 0, and we're saying that this del Q has to be, it exists, it's admissible, as they say, that means this expression has to be equal to 0. That means tau minus JTF has to be equal to 0, where if that's the case, that means tau is equal to the transpose of the Jacobian times F. Okay? Now, do you need to sit down and study this at great detail? I'm never going to ask you to derive an equation. That's not what this course is all about. But the point is, what is important is to realize that if I have some forces and torques at the end effector, when that end effector is applying, touching the world, touching the wall, touching the table, and doing stuff, there is a static component to all that. And we can calculate, for static conditions, the reaction forces at the joints are going to be this set of vectors tau. For 5 joints, tau is going to be 5 by 1. 6 joints, it'll be 6 by 1. And the F is always going to be a 6 by 1. There are going to be 3 forces and 3 torques. And essentially, to figure out what these reaction joint torques have to be, what does the motor have to overcome under static conditions, we basically multiply the transpose of the Jacobian times F. Now, just looking at that and trying to understand this a little bit, what you need to remember that Jacobian changes its value depending upon where you are in the workspace. So Jacobian is always a function of the joint variables. And because it's a function of joint variables, what that's telling you is that the reaction torques at each joint are going to be different if I am pushing at the wall here, or pushing at the wall there, or pushing down on the table, because we're going to have a different set of joints. Still the same work volume. The origin of my robot is over here. Whether I'm doing this or doing that or doing whatever, I have a different set of joint variables, and so the reaction forces that I'm going to get at each joint is going to change depending on the position of my system. And F essentially is, we're assuming there is a force torque sensor that's measuring these reaction forces in some experiment in order to calculate what those reaction forces are at the joints. So let's take a look at a very simple example, just to take a look at an example that we've looked at before. And this is essentially a two-link robot, planar robot, only moves in the plane. Here's theta 1, there's theta 2. There's a torque applied in this robot at the first joint, a torque applied at the second joint, and assuming over here at the end point, in this time, before we looked at it being two components, velocity along x, velocity along y, now we're basically saying if there is an fx and an fy, if we measure the force in the x direction and the force in the y direction that this robot is applying to a particular surface. If we do that, can we calculate what the two torques are for a particular set of theta 1 and theta 2? And so we previously went through and I showed you what the Jacobian of this two-link thing. And by the way, it's in your textbook. If you go back, I give you the exact problem numbers in all three editions of the book. This is what the Jacobian looks like. And remember, S sub 1, 2 is the sine of joint angle 1 and joint angle 2. And if this is the Jacobian, essentially the transpose of the Jacobian, remember the diagonals stay exactly the same. We just swap the off-diagonal terms for a 2 by 2. Very simple transpose. So if we take the transpose of this, we get this matrix. Here is fx, fy. And if we basically multiply these two terms appropriately against fx and fy, we're going to be able to calculate what tau 1 is. And if we multiply minus L2 S12 times fx plus L2 C12 times fy, we are going to get tau 2. So we're able to calculate what must the two joints, what must the two motors, how much torque do they have to apply. And again, it's going to vary all over the place depending upon what theta 1 and theta 2 is. And you can actually calculate it by plugging in joint angles in order to calculate the torques. Again, remember, we're not talking about dynamics. Everything is stationary, and everything is rigid for all this to apply. And you can, again, I just repeat down here what where you can find the derivation of the Jacobians. Okay, so let's now do another example. This is example 1. And we're going to take a look at example 2. We're going to look at more complicated worlds. And the more complicated world we're going to look at, we're actually going to look at a force torque sensor and a much more complicated geometric relationship. And so again, this is simply defining the relationship between the small variables in P, which are the end effector displacements. So this is a 6 by 1. There's going to be 3 small translations and 3 small rotations, and at the end point. And it's related to small displacements at the joints. And the size of this vector is basically a function of how many joints there are. And then there's the Jacobian that relates del P with del Q. Okay, that's the famous Jacobian. And what we're going to take a look at is an example where we're going to have a load cell, a force torque sensor. And we're going to use the force. We're going to take a look at the Jacobian and see how we can use that Jacobian to actually relate the forces and torques in the load cell, which may be sitting in the wrist of the robot, just like it is on the UR5s that you're using in the lab. And we're going to see if we can calculate what the relationship are between the forces and torques at the tool end and related to what we can measure inside the load cell. So let's take a look at this example. And in order to understand this better, I actually brought a load cell here. And I am going to pass it around. This is a very old load cell, one of the first that was actually put together. My guess is in the early 80s. Actually, if I remember correctly, property ID tells me that I got it in 1983. So it tells you it's pretty old. But what's important, and I'm going to have to draw something. And by the way, there is in your textbook, it shows what's called the Maltese cross. But before I do the Maltese cross, let me do a quick diagram. And this is important to better understand what you see. Oh, here we go. How many of you have all of you have touch strain gauges, right? You all know about strain gauges and beams and putting, if I have a beam with a square cross section, and it's just a beam with a force at the end, and if I put load cell or strain gauges on all four sides, I can basically relate okay, if I put strain gauge here and strain gauge there on all four sides, and then I apply a force, I can essentially resolve the components using these load cell, Wheatstone bridge, differential amplifier. I don't want to get into all the details. I'm assuming you've picked that up somewhere. But one way to actually get all the forces and torques is essentially, now here you're going to have to bear with me. Let's say I have 4 beams that are going to connect to this piece over here. And then we are basically, if I apply a load into the screen and everything on the outside is rigid, and I have put sensors here on all 4 sides of what might be called a multi-cross design, what's going to happen? If I press down, let's call that the Z direction, I will basically be able to calculate what the forces are by taking into account what's going on all 4 sides. If I put a torque in this direction applied to here, if I apply a torque, this will bend a little this way, this will bend, this will bend, this will bend. And essentially, again, I can resolve what that torque is. And if I put, again, it's a lot more complicated than I'm describing, but I can essentially measure by putting the strain gauges and designing them appropriately, I can essentially resolve Fx, Fy, Fz, and 3 torques that are applied to this unit. And what you see here is an early version of a load cell, but it doesn't use the cross design. It actually uses a kind of a twisted setup. And I'll pass this around so you can see what's going on. But the forces that are measured are, it's not really forces, they're displacements, very small displacements that are measured by the strain gauge. The strain gauge is giving you a measure of the displacement. And so you can relate that because these are rigid metals. This one's aluminum. You can get a relationship between force and delta x depending on the stiffness of the material. And so what this is doing, it's relating the forces and torques on the central core with the base, which is the outer ring. Okay? And this, I've removed it, but it basically fits in between here. If I left it in here, you wouldn't see what's down in here. But all the electronics for processing everything in here, today we use semiconductor strain gauges. It's a whole different world of what goes into a load cell compared to the 80s. Today it's a whole different world, but you need clean rooms to design them and build them. But this thing fits in between here and here. But what's more important is this outer ring is essentially one end, let's say, connected to the base. And then this inner ring is either pulled or twisted compared to the outer ring. So this piece basically attaches to the central core over here, and it basically pulls or bends and torques, and you can measure that all with this setup over here. And it was a pretty, back in the late 70s, This was late 70s, early 80s. This was awesome. Today, we are dealing with totally different technology. But just to give you an idea, I have much more recent load cells, but I don't have them apart. What's nice about this is you can actually look at it and touch it and feel it and see what's going on. So I'm just going to pass this around. And so I think there's enough time to make it to the few people who are here. So look at it closely. I'm trying to remember what chapter in the textbook. You just look through the chapters. I think it's chapter 10 deals with load cells and this force torque kind of analysis. So you can see this. So I put this, I wanted you to see a load cell before I put this on the screen. And in the lab that you're doing right now, lab number 4, there is a load cell. Robotic makes those load cells. They do a pretty good job, relatively inexpensive. Relatively inexpensive. Anyone care to guess how much a good force torque sensor costs? Are we talking hundreds of dollars, thousands of dollars? I'm not asking for exact numbers. Thousands, absolutely. We're talking thousands of dollars. Why? Because we're talking about very tiny displacements that we're measuring. And so you have to have very significant amplification in there. So we have differential amplifiers that are amplifying these very small changes and having very high gains with very small displacements. You're often going to pick up all sorts of other signals. Your load cell becomes an antenna, and it will even pick up, the air is filled with what frequency is all over the place, whether you can sense it or not. Anybody built any little circuit with a high gain? 60 hertz. So if you're in this country, in the US or Canada, you're going to see 60 hertz all over the place. If you go to Europe, it'll be 50 hertz. Don't ask me the history of why there's a difference. But the bottom line, so you have to have notch filters in your differential amplifiers that remove that 60 hertz. Otherwise, the other thing is strong radio signals. Nowadays, everything is Wi-Fi and I'm not sure what the frequencies that are being transmitted, but you need to make sure when you have extremely high gains that you filter out all the other stuff. And that's what has to happen with good high-quality force torque sensors. The whole mission is very tiny displacements are measured, and they give you an idea of what the forces are. All right? Just like I said, that del Q is extremely tiny, and the smaller they are, the better the result. But the stronger the materials you have to use in there, and you have to make sure you never go elastic. What does that mean? Or plastic. You want to stay in the elastic region. That means the strain, the force-torque relation, the force relationship to displacement has to be linear. If you go beyond, the yield strength essentially becomes plastic and it deforms permanently. You might as well throw that load cell out. So in good design, what's often done in a good load cell, the beams can move up and down, but they're typically going to be stops on both sides so that you can push them down in one direction, but it will hit a stop so that you can't overload it. So when you buy a force torque sensor, you want to make sure that they tell you what the maximum forces and torques you can apply. If you apply larger forces and torques, it will bottom out and will not allow it to go into the yield region. Okay? That means because if you overload it, typically you have to throw out a $5,000, $6,000 load cell. You don't want to do that. Okay? So make sure. What's the other important parameter that you need to worry about when buying force torque load cells? Crosstalk. What does that mean? Essentially, if I'm measuring just assume forces in this direction, forces in that direction, and forces in that direction. When I apply a load in this direction, I may end up with small displacements in, if this is z, I may end up with small displacements in x and y. So when you buy a good load cell, you have to look at a couple of things, but the crosstalk is important. And typically you want to make sure that what you measure in Fx is no more than 3% of what's in Fz. Okay? So that even if there's no Fx, you want to see 0, no matter what Fz is, right? But there is going to be some cross effect, and that cross-coupling effect, you want to make sure in a high-quality design, typically the number should be under 3%. So if Fx should be 0 and you see 0.03 of Fz on it, that should be the maximum for a reasonably good design. Okay, so keep that in mind. We're going to go, I have a whole bunch of websites we're going to explore. Looking at the time, we're not going to get there today, but we'll take a look at different manufacturers of load cells and what they sell and what you do with these systems and all sorts of videos, but we won't get to that till next Tuesday. Today, I only have a few minutes left, so I'm going to do this rather quickly, just to show you the concepts. Here is my load cell, and it has its own coordinate frame, which is UVW. That's the coordinate frame. And there's small, there's a d phi v, d phi w, and d phi u. These are small little rotational displacements about the coordinate frame. So again, this is a sensor. There's a du, which is the small displacements along the u direction. dv are small translational displacements along the v direction. And dw are small displacements in the z direction. Again, when you buy a load cell, it will tell you exactly which direction is Fz, Fx, and Fy. It'll be marked on the outside of that sensor. And so all measurements in that load cell are essentially going to be in terms of the UVW coordinate frame attached to the load cell. But when then I mount that load cell in the wrist on the flange of the UR5, you can see it over there. Take a look at the next time in your lab. It's essentially, it's black, not very colorful, but it is in between. And if I remember correctly, those cost about $4,000 to $5,000 a piece. And today, when you buy a load cell, almost all the processing is inside the load cell itself. Okay? It used to be that with the ones that are passed around, there was a whole other box on the outside that had to do more of the computational processing. That was not, no matter all the electronics you see there, there's a lot more stuff going on in a box on the outside. So essentially, we can buy little load cells with a ton of processing inside, and essentially, it is really measuring strain. Remember, strain is the d phi v, d phi v and dv, d phi w and dw, and d phi u and du. And then the load cell translates that into f in this case would be fu, fv, fw, and you're going to compute the torques about u, v, and w. So that's the output. This is what you're going to read by your computer when you take the output of the load cell. But now I have an end effector, and it's holding a tool, a wrench. And there's a bolt head over here. And so this bolt is going into some type of a tool object. And you now want to apply a set of forces and torques to the tool. And at the tool coordinate frame, let's call that the world x, y, z. So essentially, x, y, z is the coordinate frame on the tool itself. And there are going to be small orientational changes that are taking place, d phi x, d phi y, d phi z. And what we want to know is if we have a relationship between the displacements in one coordinate frame with the displacements in this other coordinate frame, and that relationship is the Jacobian, then I will then have a relationship between the forces and torques using the transpose of the Jacobian. Does that make sense? And so given it's 9:55 already, I basically show that what d phi u is equal to d phi x when we do the coordinate transformation. R is a vector from this origin to the origin of the UV of the sensor's coordinate frame. It has an Rx, Ry, and Rz, which you see over here. And so this is the tool coordinate frame. This is the sensor coordinate frame. And in this particular case, in order to make the analysis, I won't say trivial, but less complicated, we're looking at a case where UVW is aligned with XYZ. That means U is along X, V is along Y, and W is along Z. And that allows you to go through this particular analysis. And I don't want to, essentially, if you do the moments, you are going to get this relationship, which turns into this equation. There's du, dv, dw, d phi u, d phi v, d phi w. It's going to be equal to dx, this matrix, which is a 6x6 matrix, times d sub x, dy, dz, d phi x, d phi y, d phi z. This is a 6x6. This is an identity, a 3x1 identity matrix. All the off diagonals are 0. This is also an identity matrix, a 3x3. All the off diagonals are 0. There's a diagonals of 1 here. And this 3x3 is all zeros. And this is the most interesting part of the Jacobian, which multiplies each of these terms. This is the Jacobian. Okay? I don't want to go through all the detailed steps. I'm just showing you that this is the relationship between the sensor small displacements, that's the strain in the sensors, and this is the strains at the end effector where the tool is doing its particular job. And so dp is equal to j dq, and next Tuesday we just take the transpose and out pops the relationship we need, and then we're going to take a look at all sorts of applications, different load cells. You typically don't have to calculate all this. It is often done for you, again, depending. Certainly, the load cells give you, they work out the Jacobian, so you don't need to. But it does not know where the tool is, so then in that case, you have to add your own analysis to come up with what you need. Thank you very much. Sorry I went over a few minutes. We'll pick up on this next Tuesday. And I'll be meeting with a bunch of people after class, and you all know who you are. Thank you, and we'll see you all next Tuesday. And again, if you have any issues with the exam, please first talk to Robert. And if he can't help you, you come see me. Just shoot me an email, and we'll set up a time. Thank you.
I'd wait till the end just to bring it up.
Okay, thank you. If you hadn't brought it up, I would have walked out of here with a